Okay, good afternoon. So I want to start out just talking kind of broadly about what we've done so far and where we're going. So far, Chapter 3, histograms, Chapter 4, summary statistics, average, median, standard deviation, and Chapter 5 did kind of a special case of a histogram when things look like the normal curve. We could do a bunch of stuff. Okay, so we talked about converting to standard units, using the normal table, all that. And then the handout kind of revisits average and standard deviation with summation notation. So we can manipulate things, I hope, a little bit more easily using summation notation. And do a little bit, these other kinds of problems that you did on your last homework. So that's where we've been. All that is stuff that has to do with one variable. Where we're going is stuff that has to do with two variables. Okay, so we're skipping Chapter 6 and 7. Chapter 6 has to do with, I don't know, kind of a specific application of some of the stuff we've done and some examples. Chapter 7 has to do with plotting points and lines, which hopefully is review. And Chapter 8, like I said, starts talking about two variables. So we'll talk about both pictures, meaning graphical summary statistics or graphical descriptive statistics for two variables, and also new summary statistic for two variables. Okay, so that's sort of where we're headed. I just wanted to mention with the quizzes, so the quiz was posted yesterday on BSpace. That quiz will be due the following Monday in section. And you also have a regular homework. I haven't posted the homework yet, but I will by the end of the day. Okay. So what you should, and that homework will include the handout for Thursday's lecture will have next Monday's homework on it. So my intention with the quizzes, as I said on BSpace, but I'll just say again quickly, is that you not spend a ton of time on them. I feel like the intention of this is a little bit kind of self-diagnostic. These are harder problems. This is, I don't really necessarily expect, I don't expect people to get them all right, but I think you should challenge yourself a little bit to try to do this without spending a lot of time, without using the book, and sort of see what you know, having been to lecture and done the homework and stuff like that. So that's my intention. So I hope that it's not, you shouldn't add a lot of time to what you're doing this week. You get full points for purposes of your final letter grade. You get full points on the quiz if you get at least 5 out of 20 correct. Okay. So again, it's not intended that you, spend a lot of time on it necessarily. You don't have to get it all right to get full points for your letter grade. Yeah, so I hope that you sort of take it that way and treat it as something that you're using as a diagnostic tool. Okay, questions about the quiz, homework, anything else going on? Okay, so like I said, we're moving into working with two variables. The first thing I'll talk about is a picture. So for two variables, like I said, for one variable, our picture is the histogram. Summary statistics are average, median, and standard deviation. For two variables, first thing we'll look at is what's called a scatter diagram or a scatter plot. Is really just what you would think is a plot of all the points for your two variables. Okay, so let me just draw, well, actually, let me draw one quick picture here. So suppose we wanted to look at a plot of height and weight for a bunch of people. So put height on the x-axis and weight on the y-axis. And each person has a height, has a weight, so we have a bunch of dots, right? And you draw, a dot for each person. I drew a rough picture like this, I think the very first lecture, right? And generally you see that tall people tend to be heavier, but it's not true for everyone. So, some people are, tall and skinny. Tall and skinny is sort of down here somewhere where people are tall, but maybe not as heavy. And then short, fat people up there, and so forth. Okay. So roughly speaking, when I draw scatter diagrams, I'm not generally going to bother drawing all the points, okay? So as a kind of shorthand for that picture, I'll draw something like this. Okay? And this is represent to roughly outline the outside of the points, okay? So this is meant to represent the same thing as that, of height and weight, but it's a little bit neater and quicker to draw that way. Okay, so that's like I say, typically the way I'll draw scatter diagrams is that's sort of a shorthand for lots and lots of points. So I don't mean that all these people are on this oval shape. I mean that there are lots of points in here. Okay, so let me just name a couple of kind of landmarks. This is the average of x, and this is the average of y. That point is called the point of averages. And just to kind of connect this back to one variable, I've given you the summary statistics for x and y of at least one summary statistic, the average. And I'll say one more thing about this, which is that just like with one variable, if x roughly follows the normal curve, so if the height of people roughly follows the normal curve, you can still say that about 68% of the people are within 1 SD of the average, just like we would talk about in chapter 5. If you want to think about what that means in terms of this picture, well, if you went average plus 1 SD here, and then maybe average minus 1 SD here, it means that about 68% of the points are in between those two points. Okay, 68% of the x values are in between there. So roughly about 68% of the points should be in there. Okay. Okay, so about 68% of the heights should be in this shaded region. And this is assuming that things are roughly normal. Okay, so when I say assuming heights roughly normal, I mean that the histogram for the heights by themselves roughly follows the normal curve. Okay, so if you look at a sort of way to think about that backwards, is if I just showed you the scatter diagram, if I wanted to kind of roughly guess what the SD is, I sort of want to go out a certain distance until I think, okay, I've got about 68% of the points. It's about 2/3 of the points. So the standard deviation should be about that big. Okay, so just kind of thinking about that backwards. About 95% of the points should be within 2 SDs. So that should be just about to the edge of the picture. Okay, questions on the scatter diagram? Yeah. Because it's plus or minus 1 standard deviation. So all I'm saying there is basically the chapter 5 idea that about 68% of the points should be within 1 SD of the average. But the same, she said it's not a histogram. Well, that's true. This is not a histogram, but it's still true that about 68% of the points should be within 1 SD of the average. That's just if heights roughly follow the normal curve, then about 68% of the heights should be within 1 standard deviation of the average, whether I'm looking at a histogram or a scatter diagram, or really, I don't even need to look at a picture. It's just a sort of, I don't know, concept that if I just give you a list of numbers, if they roughly follow the normal curve, about 68% of them should be within 1 standard deviation of the average. Okay? Yeah? Different SD for each axis. In fact, in this case, it's different units, it's different scale, right? Yeah. So a lot of the pictures in your book, when you look in chapters 8 and 9, a lot of the pictures are converted into standard units. So if you want, you could think about this converted into standard units. And if I drew an axis in standard units, it looked like that. And then everything sort of looks the same, right? If I'm just looking at pictures that are in standard units, the center, I mean, the point of averages is just 0, 0, because the average is 0 in standard units. One SD above average, one SD below average, and then sort of same thing for the y-axis. Okay? So a lot of the pictures in this part of the book are drawn in standard units, although they don't have to be. These are heights. Maybe the average height is for a bunch of adults, maybe 5'6", SD about 3 inches or something. And then here, I don't know what the average weight of people is. 150 pounds, I don't know, something. So, okay, yeah.
Is there any particular way to know whether or not a set of data is like normal and thus would follow the characteristics of the normal curve?
Okay, it's asking, is there any way to tell if the data follows the normal curve? Well, the simplest thing to do is just to look at a histogram and to sort of see if it looks roughly like the normal curve. Now, if it doesn't, if you're sort of concerned, well, maybe it doesn't look exactly like the normal curve, well, these things are going to be approximately true. If you use the normal table on data where the histogram doesn't look exactly like the normal curve, but it's pretty close, well, then your answers will be pretty close. Okay? Anything you look on up on the normal table will be pretty close. So for the purposes of this class, I'll generally either tell you, or you might be, if I don't say anything about it, you might wonder, okay, and maybe either try to determine whether or not you think it follows the normal curve, or say something about it. Say something about your answer about, well, if this follows the normal curve, then this is true. So I'll make one more comment about a way to tell if things don't follow the normal curve. If data is kind of fairly badly skewed, often a problem that will happen is that if you go 2 SDs to either side of the average, you'll get into an area where there isn't any data. So for example, if I have a bunch of incomes and the average income is $50,000 and the standard deviation is $30,000, 2 SDs below average would be negative $10,000. So presumably there aren't people that have that as an income. So if the data followed the normal curve, you'd expect that there would be some people 2 SDs above, 2 SDs below. So the fact that income for this hypothetical data set with average 50,000, SD 30,000, the fact that no one is 2 SDs below average is a problem. That means that the data can't really look like the normal curve, right? The normal curve would have at least some people down there. Okay? All right, so that's one way you can tell that things are very bad. For things that are not very bad, yeah, if your answers are, if it doesn't quite follow the normal curve, your answers will be off by a little bit. Okay? Other questions or thoughts on that? Okay, so the point of drawing pictures, so histograms in chapter 3 and scatter diagrams now, is to be able to tell something about the data relatively quickly. Again, if I gave you just a list of a bunch of heights and weights for people, it might even be difficult just to tell that tall people tend to be heavy, right? If I just gave you a bunch of, this long list of a bunch of people's heights, a bunch of people's weights. You have to sort of look at it a little bit. Here you can tell it quite quickly. You see the picture, well, taller people tend to be heavier. So that's one part of the use of drawing these pictures. Yeah, so again, like I said, another thing is if you think about the summary statistics, you can tell a little bit about the percentage of people in a certain range, either vertically or horizontally, okay? Which that information you could get equally well, or maybe a little bit easier even from a histogram, but that information is still in this picture. Okay? So, questions? Okay, so that's that. Okay, so I want to talk about a new summary statistic, which is the correlation coefficient. Often the word coefficient is just left off. We just talk about the correlation between two variables, often abbreviated with the lowercase r. And the correlation coefficient measures, I'll give you kind of a technical textbook definition first. Measures the strength of the linear relationship between two variables. Okay, so that's, like I said, it's kind of a technical, I don't know, slightly technical definition. A little bit more intuitively, you might think of this as measuring how close the points are to a line. Okay, so correlation is something you can calculate based on two variables. I'll tell you how to calculate it in a little bit. I want to talk a little bit more about what it measures and what values you might get. So correlation is always between -1 and 1. And I'll talk a little bit about the kind of extreme cases or special cases first. If r is equal to +1, that means the points are all on a line. With positive slope. Okay. If r equals -1, the points are all on a line with negative slope. Okay, so those are sort of the most extreme cases. R equals -1, you might think of as being like, and it doesn't have to be a slope of -1. It can be like that or like this. And I don't know, you might think of that as being the x and y values sort of hate each other. They always do the opposite thing. When one of them goes up, the other one goes down, right? Whereas the r equals 1, you might think of the variables as being like BFFs. They're like always doing the same thing. And whatever one does, the other one does exactly the same thing. Okay, tried. Yeah. I'm sorry. Pause it. Right. Okay. So so these sort of behave exactly the same. If one of them goes up, the other one goes up. These are both, you might think of both these as sort of being perfectly correlated in that they're on a line. You always know if you know one of them, you know what happens to the other one. Okay? Okay, so those are the most extreme. Any questions about those? Okay. Okay. So r equals 0 is sort of like right in between. And you might think of this as being uncorrelated. So the typical pictures that I might draw for this, you might just think of it as like a 0, that there's no particular linear relationship. If one of them if you have a large value of one of them, there's no reason to think that the other one will be either large or small. You can draw a lot of pictures with dots that will give you a correlation of 0, actually. You could do something like this. So it's sort of symmetrical. There's no tendency for y to be large when x is large, or vice versa. There's no particular line that I could draw through these points which describes the points very well. Okay? So you could do things like that. You could draw like a triangle if you wanted to, like this. That would have correlation 0, as long as the average of those two values is the same as that. Okay, so sort of, again, symmetrical. Okay? So questions about those cases? Yeah.
If it's a horizontal line, would it be 0 also?
Yeah, the question is, if it's a horizontal line, would you consider the correlation to be 0 also? Yeah, so that's a little bit of a silly case. Either a vertical line or a horizontal line means that only one of the variables is changing, right? If all the points are on a horizontal line, it means that the y value is always the same. So you wouldn't even really study that ever, right? You don't really have two variables. It's though everyone has the same weight, for example, okay? So it's not really a case that you would study ever, okay? But yeah, that's right. Okay, any other questions? Okay. So in between, I've sort of drawn one case here with a positive correlation. So in between, let's see. Let's see, sorry. Okay. So that picture there might have a correlation of, I don't know, around maybe 0.6 or so. So this is height, weight. So r is bigger than 0, perhaps 0.6. Negative correlation, one example would be for if your data was based on cars, if you had age of cars versus price. So this is for cars. In general, as cars get older, they decline in price. I'm sort of ignoring special cases of like fancy antique cars and things like that. But in general, if you think about the cars that are on the road, most of them will follow this pattern that the older cars will be worth less money. Okay, so that's a negative correlation. Just to throw an example up there. And I want to say one last thing, sort of summarizing this idea. Which is that correlation doesn't have any units. So what I mean by that is that it's not like a correlation of 0.5 is like halfway close to a line or something like that. So R has no units. And like I say, it's like, I mean, if you want to think about what it measures, it's measuring how close the points are to a line in some way. So it's not like, a correlation of 1 means they're all on a line. You can't, well, like for example, if I had a correlation of 0.2 and a correlation of 0.4, 0.4 doesn't mean the points are twice as close to the line as a 0.2, okay? It measures something about how close they are to a line, but you can't really kind of pin it down in that way, okay? So measures linear association is another way that it's phrased, okay? And if you want to look at some pictures of different correlations, kind of get a feel for what they look like, there are pictures in your book on pages 127 and 129. Okay? And that gives you a bunch of pictures. And the pictures that are there are scatter diagrams that are all in standard units. So they're all kind of, centered at 0, 0, and you can compare just kind of the raw pictures themselves. So the correlation is a summary statistic that describes something about the picture. It no longer has units like height and weight or anything like that. So if you want to think about two pictures that, if you have two pictures that look the same, regardless of what the units are originally, those two pictures will have the same correlation. Okay, so you sort of think of correlation as being a feature of the way the picture looks. Okay? All right. Any questions more about any of this? Okay, so let me do a calculation. Show you how to calculate it. Okay, so to calculate R, first step is to convert both x and y into standard units. And this can be time consuming. So remember, standard units, you need to take the value, subtract off the average, divide by the SD. And you need to do that for every x value and also for every y value. So, you know, sort of annoying to do it for more than 4 or 5 points or so. But, you know, you can. OK, so that's step 1. Step 2 is to multiply or take the product of the standard units. And I'll just label this xu of x times su of y. So that's the standard units of x times the standard units of y. So each person, for example, for the height and weight, each person has a height converted to standard units. Each person has a weight converted to standard units. So for each person, you take that product, and then take the average of the products. Okay, so the average of the products is R. All right, so it might not be obvious that that should give you anything useful or that it should measure how close the points are to the line or anything like that. Let's do a calculation, and then I'll talk about why that calculation makes some sense. Okay, so these x values are the same ones that I have dealt with for the last couple lectures. So I know the average and the SD of these. And the y values I'm going to use are the same, but in a different order. OK? So 1, 3, 4, 5, 7 for x, and then 3, 1, 5, 7, 4 for y. Like I say, I know the average and the SD for both those lists. And I'll just maybe write it down here. So the average of x equals the average of y. And that's 4. And the SDs are also the same. SD of x equals SD of y. Those are both 2. Okay. So I just know that from calculation last lecture. I guess both of last lectures I calculated the SDs. OK, so then first step is to convert x and y into standard units. So I'll just show you like 1 or 2 of them. So standard units of x. Standard units of y. Okay, so since the average of x is 4, standard units here is going to be 1 minus 4 divided by 2, right? Just the value minus the average divided by the SD. That's minus 1.5. And for y, I'm going to get the y value, same average of 4, same SD of 2. This is minus 0.5. Okay? So I'm not going to write down all the calculations. I'll just tell you what they are. And actually, these numbers are fairly nice. So you might be able to just see it, right? Like 3, the SD is 2. So the average is 4. 3 is 1 below 4. So it's half an SD below 4. OK? Or you could just do the same calculation again. Take 3 minus 4 divided by 2. 4 is right at the average. So in standard units, that's 0. 5 is half an SD above average. And 7 is 1.5 SDs above average. So again, you can sort of think about it intuitively or do the math. This one, the 1 for the y value is 1.5 SDs below average. 5 is half an SD above average. 7 is 1.5 SDs above. And 4 is right at the average. OK, so then that's step 1, convert everything to standard units. And this made my life a little bit easier because I had already calculated the summary statistics. Okay? But in general, you need to do that too on the way. And here are the products. Step 2 is to take the products. So minus 1.5 times minus 0.5 is plus 0.75. And then, again, minus 0.5 times minus 1.5 is 0.75, 0, 0.75, and 0. OK? So I'm just taking the products across. OK, any questions up to now? OK, so finally, the average of these, the sum of these is 0.75 plus 0.75 is 1.5 plus 0.75 is 2.25. So R is 2.5, so wait, 2.25 divided by 5, which is 0.45. Okay? So that's a calculation of R. If you want to think about that a little bit intuitively, it's generally true that the larger x values tend to correspond to the larger y values. Okay? These points are not on a line, so it's not going to be a correlation of 1, but you sort of think intuitively that it should be somewhat positive. So I'll draw a picture and talk a little bit more about why, or kind of why that calculation makes any sense. OK, so the x values and the y values are both 1, 3, 4, 5, 7, just in a different order. So the points are 1, 3, 3, 1, 4, 5, 5, 7, and 7, 4. OK. So you can kind of see that there's a somewhat positive correlation, meaning above average values of y, above average values of x tend to correspond to above average values of y. Sort of a tendency up there. Now, in terms of thinking about what the calculation is doing, I just want to draw lines through the averages. Okay, so there's a vertical line through x equals 4, the average of the x, and a horizontal line through the average of y, which is also 4. So now let's think about what's going on in the calculation. What we do, first of all, is to convert everything into standard units. So if you have points up here in this quadrant, actually, let's think about it this way. Everything to the right of this line is above average for x. If it's above average for x, it has to be positive in standard units for x. If it's to the left of that line, it's going to be negative in standard units for x. Okay? So if you then think about what's happening with x and y, we're taking the product of the standard units. Right? So 1 and 3 are to the left of the line. They're negative in standard units. 5 and 7 are above average, so they're positive in standard units. 4 is right at the average, so it's 0. And then we're going to multiply that by the standard units of y. And similarly, if you're above this horizontal line, the y value is above average, so the standard units is positive. And below that line, the standard units of y is negative. So when we take the products, if we're somewhere up in this quadrant, x is above average, since we're to the right. Y is above average since we're above the line. And the product is going to be positive then, right? Because we have a positive x value in standard units times a positive value for y in standard units. So I'm just going to draw a plus sign up there. And that corresponds to this one, right? 5, 7 is that point. It's above average for both x and y, so the product is above average, or the product is positive. Down here, x and y are both below average, right? So x in standard units is negative, y in standard units is also negative. So when we take the products, we also get points down here which have positive signs. So what I'm putting in those quadrants is the sign of the products, right? So x and y are below average, product is positive. X and y are below average, product is positive. Okay? Down here, now we didn't get any points down here, and we didn't get any products that were negative. But here, x is above average, so positive in standard units for x, negative in standard units for y. When we take the product, anything down here is going to contribute a negative product, and up here also a negative product. So then when you go to calculate r, it's kind of this battle between the points in the upper right and lower left. Those contribute positive products. Upper right and lower right and upper left contribute negative products, and whichever side wins, that's the sign that correlation is going to have. Okay, and the more you have things in these two quadrants, the more highly positive the correlation is going to be. So if you have the points like close to a line, if you have something like this, where there's almost everything is in those two quadrants and almost nothing is in the other two quadrants, that's going to be a strong positive correlation. It's going to be very, like, getting close to as positive as you could get. And as you kind of go towards a more, slightly more symmetrical picture, this correlation will be a little bit positive, but not very much, because it's fairly even, right? Now, why should it be 1 when you get the points to be on a line? I don't really have a good intuitive way of explaining that. I can do it really quick for this example. It's pretty quick to do. But you might think about making the correlation as big as possible. What you'd want to do is match up the biggest x values with the biggest possible y values. And if you did that, then you would get the correlation to be as big as you possibly could, right? If I had the 1.5 here and then a 1.5 here, match them up, put them in the same order, then that's going to make my correlation as big as I possibly could. So let's do it for this example. I'll mix them up and show you what happens if the correlation, what happens if they are on a line. This is not intended to be a proof or to absolutely convince you that it should work, but I think it's at least a little bit surprising that it does work. So if I just take x and y, both lists are the same, 1, 3, 4, 5, 7, 1, 3, 4, 5, 7. Standard units for x, standard units for y. So this is exactly the same as the standard units for x over there. And standard units for y are just the same. So take the products. Minus 1.5 times minus 1.5 is 2.25. And then minus 0.5 times minus 0.5 is 0.25. And then I get a 0, 0.25, and then 2.25. OK, so add them up. 2.25 plus 0.25 is 2.5, and then another 2.5. So the sum of the products is 5. And then I get r's. The average of those products is 1. OK, so it works for this particular case. And if you want, you can check it for any points that you want to put on a line. Again, this is sort of, I'm trying to at least intuitively explain that you couldn't do any better, right? There's no way to make the correlation any bigger than this. I'm matching up the points as extremely as I can so that when x is as extreme as possible in standard units, I multiply it by something that's as big as possible for y. Okay? So if you do that, then you end up getting a correlation of 1. Okay? So, yeah, question? Why is it that r can't be larger than 1? Well, you might think of it as it's how standard units work. I guess I'm trying to at least illustrate that in this example, there's no way that you could. This is extreme as you could possibly make things, right? There's no way that you could rearrange the points to make the correlation any bigger. You can, if you want, you can think about it in terms of, actually showing that is, I don't know, a little bit more algebra that I really want to do. But once we do summation notation, you can kind of see what that would look like at least. So we're going to do summation notation for correlation on Thursday. And then you might be able to see a little bit more why this ends up being that. So, OK? Maybe I'll comment on it when I show you the formula for correlation, too. OK, questions on this? OK, so let's take a little break. So this is basically the end of chapter 8, more or less. OK? So I'll talk about a few little concepts in it again, but that's basically it. Okay. Okay, so I talked a little bit about why we might want to draw a picture for data. Like we can tell things like, okay, when x is large, y is large for heights and weights, and we can say a little bit about data based on picture. I wanted to give you a kind of real world example that's always been one of my favorites. I guess I first saw this data as a graduate student. It was a computer lab to analyze this data basically and try to like draw some conclusions from it. And I thought it's an interesting example. It's I don't know, you might think of it as a historical example. It's not super old. It has to do with data on the space shuttle. And this is data that was collected before 1986. So 1986, Space Shuttle Challenger kind of famously blew up. Another reason why that particular flight was famous was that it was the first time that we attempted to put a teacher on the space shuttle, unfortunately. Yeah, so it's sort of a famous, I don't know, accident in NASA history. Like I said, this is data that was collected beforehand, and what happened in that accident is that something called an O-ring failed. So an O-ring is like a big ring. And the purpose of the O-ring is to maintain a seal where gases might escape. Okay, so the idea of putting the space shuttle out there is, you burn at a very high temperature, very high pressure, and you shoot things out of the back of the rocket, and the rocket goes up, right? So where that rocket attaches on, you need to maintain a good seal so that gases don't escape out the side. So if you look at footage of that accident, the shuttle goes up, looks like everything pretty much is going all right, and then at some point you can see stuff kind of shooting out the side, and it spins around crazily, and then it blows up. So what happened was that part of this ring failed, and so gases were able to escape from the side, so it was bad, right? So the data I'm going to show you is data on tests that were done on the O-ring beforehand. So they had this data going into the space shuttle launch. And let's just show you. OK, so that's what I want. Yeah, oops. Let me zoom that in a little bit. Oops. OK, so this is temperature in degrees Fahrenheit on the x-axis. And that's what I want. Here you go. Should try to focus it a little bit. OK, I guess you can read it. OK, so temperature in degrees Fahrenheit is on the x-axis, and temperature in degrees, and damage is on the y-axis. And this is kind of a semi-subjective scale that they use to measure damage. It was based on visual inspection of the O-rings. And damage of 0 means that they sort of couldn't see anything wrong with the O-ring. Higher levels of damage mean that maybe that there were like parts of the O-ring that had flaked off and whatever. It's sort of like you can imagine it as being like a really big rubber washer, okay? And it's this sort of high-tech material, and it's intended to be able to maintain a seal at very high temperatures and very high pressures, okay? So this temperature is air temperature, okay? So they did these tests at particular air temperatures, and like I say, they had damage of varying degrees. The two circled dots are cases where their sensors were, so they do this test in like in experimental conditions. It's indoors, right? It's not like the rocket's outdoors. And so they have sensors all around trying to measure what's going on. And those two circled dots, they were able to measure what they call blow-by, which just means that they detected gas escaping. Okay? So the seal failed in those two circled dots. OK, so this is a scatter diagram. What can you tell me about the data? Or do you have any questions, or what do you think? Yeah. Would those blow-by ones be considered outliers? OK, so I'll talk about the concept of outliers in a bit. Roughly speaking, outliers mean points that are far away from everything else. I would not consider them to be outliers. They're sort of in the general range of the points. I mean, that lowest one maybe you consider to be farther away, but I don't know. I guess I wouldn't consider that to be super relevant for, I guess, the point that I want to make about this. Yeah?
They had so much damage. If that one got damaged at a lower temperature, why wasn't there any other tests done at that time?
Okay, this is air temperature, and it's in Florida. So his question is, why didn't they do any other experiment? Why didn't they get any more data towards lower temperatures? This is just whatever the air temperature happened to be. They did not control the air temperature. So yeah, it's in Florida, and there weren't, this is just the day that, the days they happened to do experiments. Okay? Yeah?
Why at temperature 70 there are two four
Yeah, so some of the dots are sort of stacked up because there are multiple points at that point. So like here, there are 3 points all stacked up, meaning that this temperature reading was the same. I guess it looks like about 67 degrees, and there were 3 zeros. So up here at 70, there were 2 measurements of 4. Okay? So this just means there are multiple points there. Okay? Is that your question?
Why there's 0 and 4 at temperature 7? What's the circumstance that makes this different? Why are the same temperature?
Why are they the same temperature?
At the same temperature, but the damage to O-ring, there are 2 dots at 0 and 2 at 4.
So our question is, why are there, at 70, for example, why are there 2 dots at 0 and 2 dots at 4? It's just whatever happened to occur, like whatever damage happened to occur to the O-rings. So it's an experiment. I mean, you might think that the materials are not exactly the same in every O-ring. So some O-rings might be stronger than others. There might be other conditions that might change things, like, I don't know, dust in the room or other things. Yeah. So, yeah.
Wasn't it particularly cold on the day that the Space Shuttle
Wasn't it particularly cold on the day that the space shuttle blew up? Well, yeah, it was. Yeah. Yeah, you sort of see a negative correlation here. And even if you didn't know what correlation meant, you might sort of read into this that low temperatures are bad, right? Generally, the higher temperatures tend to have less damage. The lower temperatures tend to have more damage. But you might even be worried just if the launch temperature, I think that lowest dot is 53 degrees. You might just be a little bit concerned if you had a launch temperature below 53 degrees, right? So, yeah, it was 36 degrees when they launched. And it was 9 in the morning. So the engineers that gathered this data had a written report to the higher up people that made the launch decision. And in the written report, they advised not to launch. The report was highly technical. It didn't have any pictures. And it sort of described the dangers involved and all this stuff in kind of technical language. So this was sort of a big deal, partly because we were putting a teacher into space, and so the people that made the launch decision didn't want to delay it. They didn't want NASA to look like they didn't know what they were doing, having to delay the launch and whatnot. So they decided to go ahead with the launch, and it's also obviously disastrous. The people that gathered the data said, well, if you're going to launch, at least launch in the afternoon. Like at least launch the warmest part of the day, even if you feel like you need to launch on that day. So anyway, I think if you see this picture, you don't have to be a rocket scientist, right, to see that there's a problem here, right? That's a joke, that it's NASA, so they're all rocket scientists. Sorry. Okay, so yeah. So anyway, scatter diagrams are good to look at sometimes. I think this is a little bit, just a story about this disaster, but it is a lesson that that when you do analyze data a lot, often that you can find things by looking at pictures quickly, that you can stare at numbers for a long time. You can stare at summary statistics. Things might not be as obvious as if you just look at the picture. So this is a little bit like a life lesson to, if you have data that you can look at a picture of, you might as well take a look and see if anything pops up. Okay? I'll make a little post comment about this, which is that there was an investigation, a congressional investigation into this disaster afterwards, and there's a, I don't know, not that very many physicists are famous, but a fairly famous physicist, Richard Feynman, if you've ever heard that name, was on the committee that investigated this, and as part of his testimony, when he was talking, he got some of the O-ring material and put it in his glass of ice water, and a few minutes into his talk, his testimony, he pulled it out and dropped it on the table and it shattered. So he's making this point that although this stuff is supposed to be able to withstand a lot of stress, very high temperatures, very high pressures, but at kind of room temperature and below, when it gets cold, it gets very brittle. So anyway, that's my story. Okay? Questions, comments? Okay, so let's get back to stuff from the book and whatnot. Okay, so I'm going to chapter 9, and I might show another picture, so I'm going to leave that on anyway. Okay, so let's erase this stuff. Okay, so a lot of the pictures in the book, in chapter 8, are pictures that look kind of nice. They're like these nice oval kind of shapes. And not everything is always like that. Okay, so just like with a histogram, some things follow the normal curve, some things don't. Some things are skewed. They have like income or housing prices tend to be skewed. Not everything is so nice. So I'm going to say a little bit about what I mean by nice for a scatter diagram. I'll discuss this in more detail when we hit chapter 10 and chapter 11, but just as a kind of rough idea, scatter diagrams can have different shapes. And the case that I'll consider to be kind of nice is what's called football shaped. So it can be like, a fat football or a skinny football. It can be positive correlation, negative correlation, whatever, okay? But when I say football, and I'll talk about what I mean by football shape more technically in chapters 10 and 11, but just for now, this is one way that you could have a scatter diagram look, is the points generally follow this kind of a pattern. Okay, so other things could be nonlinear. Okay, so these things roughly follow a line, right? As one goes up, the other one goes up here. As one goes up, the other one goes down here. Nonlinear might be more complicated. So you might have something that looks like this, okay? Or if you want to draw dots, you might have a very strong pattern, like that might look like a section of a parabola or something, but they're not on a line, okay? So for these cases, correlation does not do a very good job of summarizing what's going on. Both of these pictures would have a positive correlation, but ordinarily we consider positive correlation to mean that large values of x tend to correspond to large values of y, which isn't really true here. Right? Large, middle values of x tend to correspond to large values of y here. So nonlinear cases, R is not a particularly good summary statistic, just like in some cases for one variable, the average maybe is not a very useful summary statistic. Sometimes the median is better. Okay? So same sort of thing here. Correlation is not always a good way to describe data that is not football shaped. So something like this might be the number of hours you study the night before a midterm and your grade on the midterm. I don't know this, but this is my theory, that people that study a lot, cram a lot the night before, stay up all night, tend to do not as well as people that study, some, but not a lot. The people that study the most the night before the midterm, my theory is that they don't do as well. And they may be doing it for different reasons, right? They may just have not studied at all ahead of time, are cramming the night before, staying up all night, and then they don't do as well because they're not generally well prepared, or it might be just lack of sleep and whatnot. Okay, so that's my theory. And the people down here that don't study at all or don't study very much maybe tend to not do as well either. And the people that do the best are the people that kind of, work hard and consistently throughout the semester and don't have to cram. Okay, so anyway, that's my thought on something that might look like that. Okay, another example that's not linear, or sorry, not football shaped, is with outliers. So someone mentioned this is a possible thing that's going on in that other picture. So outliers typically describe points that don't follow the same pattern as the rest of the data. And in that other data set, although there are, there's maybe that one point that's kind of far off up and to the left, it generally follows the same pattern, that the rest of the data kind of more or less points toward it. So you might have something like this, where you might have a very strong linear relationship, but then for some reason there's a point up there, okay? So that point does not follow anything like the general pattern of the other data. Or you might have negative correlation in general, but then for some reason there's one point up there or something. So there's a point or maybe a couple points that don't follow the same pattern. So when you see this in an actual data set, I don't think this is grounds to just discard that point. It might be a good thing to do to analyze the data both with that point and without that point and kind of see how your conclusion might change based on whether or not you include that data point. It might also be good to try to figure out what's going on with that point. So like for the space shuttle data, if we had a point, I don't know, maybe even farther to the left, or maybe even that point, that point, I think it was at 53 degrees and high damage level, you might wonder if that point is different from some reason, like it doesn't follow the same pattern as the other data for some reason. So that's something to think about. If you have something that's outside the pattern of the rest of the data, try to figure out why. And like I say, you might either analyze it with or without. For the purposes of this class, I really just want you to be able to kind of recognize if there is a point like that or a couple points like that that's outside of the regular pattern of the data. But the other things I'm saying are sort of, for your future if you ever end up analyzing data or looking at pictures like this. Okay, questions on any of this? Okay, so like I say, football shaped is what we'll generally study, just like we generally will study histograms that look pretty close to normal. We do want to recognize that that's not always true, that sometimes we do have skewed data. In the same way, we want to recognize that sometimes we will have these unfortunate situations where things are not football shaped, but it's not the main focus of what we'll study. Okay, so. Okay, so I want to show you another picture. Actually, before I show you the picture, I'll talk about the idea behind it, which is what's called ecological correlation. So ecological correlation measures correlation where x and y are averages or medians of subgroups. So if you think about height and weight data for like everyone in the room or something like that, you have a dot for each person, right? Ecological correlation would be if we did something like group the people in some way, okay? Like, I don't know, first-year students, second-year students, third-year students, fourth-year students, fifth-year students, so forth, where each point would represent an overall average height, average weight for those groups. Okay? So in general, this tends to overstate relationships. Relationships for individuals. Okay, so I'm going to show you a picture of some data that's like this, and we'll talk about it. There's part of what I want you to think about is this idea. I also want you to just think about this data and what conclusions can you draw from this picture, okay? So you can just generally think about that. Oh, this is also called aggregate correlation sometimes because these averages are sort of aggregates of subgroups. So this data is from Berkeley High School. And it shows median income along the x-axis and average GPA on the y-axis. So the income, so all these points are for zip codes. You can see at the top it says GPA and income by zip code, and the correlation is 0.87. Okay, so it's quite strong correlation. Each dot represents one zip code. Okay, so what they did is for everyone in one zip code, look at the median income for everyone in that zip code, and then plot it along with the average GPA for all the students from that zip code. Okay, so you can kind of see that. Yeah, what can you see from this? Anyone want to comment on this? Yeah.
So the zip codes that have like a higher median income, the kids from like, I guess from those, I guess the richer zip codes, they tend to do better in school.
Yeah, so he said that the zip codes where you have a higher median income, the students from that zip code tend to have a higher average GPA. Okay. You want to add any more comments to that or thoughts? Yeah.
Well, it looks like it almost, I mean, the trend is obviously positive, but it almost might plateau a little bit. There's a gap between sort of the middle and the upper class, but it looks like it's sort of flatter at top and kind of drops off dramatically below.
Yeah, yeah. So you might think this sort of plateaus after a certain point. So yeah, the relationship seems to be quite strong, going from maybe 20 to around the middle, mid 40s, and then the relationship is like it goes up very steeply there. And then for the very high income zip codes, the GPAs aren't changing that much. The average GPA is not that different. Okay. Anyone care to offer any social commentary, any reasons why this might be true? How does this make you feel? Yeah. Uh-huh. Uh-huh. Yeah, so she's suggesting that there are more resources in those richer neighborhoods, that maybe the teachers are better, maybe that's part of what explains this effect or this tendency. Yeah?
Also, in the lower income neighborhoods, the students probably are also having to work to help support their family.
Okay, it's possible that in the lower income neighborhoods, the kids are working, so they don't have as much time to study, do well in school, that kind of thing. Yeah?
Berkeley High School is a huge example of just like in a lot of the East Bay neighborhoods, such as Richmond and Oakland, Richmond Hills versus Richmond like Flatlands, and Oakland Hills like the Piedmont area versus Oakland inner city. There's the same difference as between Berkeley and Berkeley Hills. There's a documentary or play called Yellow Jacket on Berkeley High School that people should check out. It's like the difference between
So she's suggesting that people look at a documentary called Yellow Jacket that talks about some of this stuff about the different zip codes in the area, not just in Berkeley, but also Richmond, Oakland have maybe some of the same patterns that, we have very different zip codes in this area. I think that's part of why this data is interesting, is that a lot of different people, like Berkeley High School is a very diverse population. Right? Okay, yeah?
Do you know how many zip codes correspond with each dot?
Each dot is one zip code. Yeah. Yeah, some of them will have more students and some of them will have fewer students, but each dot is one zip code. Yeah. Any other questions, comments, thoughts? Yeah. Yeah, so she said that people from lower income neighborhoods may not think that college is maybe a viable thing for them, so high school may be a different experience for them. They may not be trying as hard to get better grades and going on to college. Yeah, so go ahead. Yeah, so kind of following along the same idea that a lot of the students in the lower income areas may be from immigrant families. They may be their parents haven't gone to college, and so they don't really see it as an option for them or something that they're trying to achieve. Yeah. Right, so I think someone else made the point about students in the lower income areas may be working, so they may not be able to work as hard at school. Even, I think it's part of what you're saying is that even in school, they may be focused on thinking about a different future and a different vocational path than the students in the wealthier neighborhoods. Okay, so I want to make some kind of global comment about this, which is that some of the things people are saying are comments about neighborhoods and areas and the zip codes themselves. Some of the comments that people are making are comments about individual students, okay? So this picture is a picture of zip codes. So I think what you read into this, based on the data, should be basically statements made about the zip codes, about the areas, the neighborhoods that people come from. One that kind of was brought up that I want to just add is that the schools have different resources, right? The wealthier areas have more resources. Now these are all Berkeley High School students, so they're all at the same high school, but the elementary schools and the middle schools that feed Berkeley High Schools are located in these different zip codes. And so before they get to Berkeley High Schools, many of these students have advantages, disadvantages going in, right? That they're coming from elementary schools and middle schools that have different resources, okay? Part of that is, what teachers, part of that is just, textbooks, part of it is like, if they have sort of recent textbooks, well, you guys know what, I guess, goes into like good elementary and middle schools and not. Okay, so comments about individuals might be somewhat true, but are not really demonstrated by this picture. The correlation for individuals is probably smaller, right? The correlation of 0.87 is a lot stronger than we might expect for individuals. So why would we use this? Why would we ever use ecological correlation? Any thoughts? Yeah. Okay, so basically he's saying if your goal is to mislead people, I think. If you're, I mean, not to put words in your mouth, but he's saying if you want to make it seem like there's a really strong correlation, if you want to seem like it's a big deal, you might think about a picture like this, which is true, I think, yeah.
Also, if you have a huge amount of data, like I think if you put a dot for all the students, you wouldn't really be able to tell any correlation. There'd just be too much going on.
Okay, so he's suggesting if you actually had a dot for every student, it would be very jumbled. There's so many dots that you maybe can't tell what's going on. I mean, I guess well, any other comments? I think I'll talk about that in a second. Yeah, so I don't know. I guess I would prefer to look at the individual dots for students. The problem is that that data would be pretty hard to get. There are privacy issues associated with both GPA and income. The overall numbers, the median income for zip codes you can get from census data and average GPA from zip codes, the school would be, relatively willing to release. Okay, they have that data probably in a relatively accessible form. But matching up those students with their family incomes, there's no real way to do that. Okay, unless you actually talk to the students themselves, and then not everyone's going to want to report that information. Okay, so not everyone is going to be willing to answer a questionnaire where they're asked, what's your household income, what's your GPA? Okay, so obtaining data like this that's matched for individual students is not necessarily feasible. And like I say, if you did try to do it, you wouldn't get very complete data. So at least here, relatively easily, we can get the aggregate data, to show the ecological correlation. You should expect, though, that the correlation would not be that strong if we did look at individuals. In fact, you could draw a picture where it could even go in the other direction. Okay? So let's get rid of that. Okay. So if you wanted to, for each of these points, like say you just had a few points like this, very strong positive correlation, but maybe that point is actually made up of a lot of individuals that look like this. Okay? So it's conceivable. I'm not saying this is what's going on there, but it's conceivable that you could even have a correlation for individuals that's going in the other direction. Certainly in general, there's a cloud going around every zip code, some cloud that gives you a much weaker correlation. Okay? All right, before I let you go, I want to talk about the last part of chapter 9, which is the idea that association or correlation is mostly what we're talking about. Correlation is linear association, remember. Association does not imply causation. So a lot of what we discussed actually in that previous example, other possible explanations. It's not that the money is directly causing the GPA to be higher. There are lots of other factors that might explain that relationship. One more that I don't think anyone mentioned is that more educated parents are likely to have higher incomes, and those more educated parents might be more likely to encourage their kids to study hard, hire tutors, do whatever it takes, right, to help their students get good grades if they themselves have found that to be a successful way for them to, get a good job or whatever. Okay? So a couple more quick examples I want to give you. One is that there's a positive correlation. So positive correlation for elementary school kids for shoe size and reading ability. Okay? So if you measure kids' scores on like a reading test and you measure their shoe size, you'll find that there's a positive correlation. Why? Yeah. Yeah. So age is what's going on here. The older kids have bigger feet and they tend to read better, right? So I think there's at least a slight pull that your mind has to think, well, why should kids with big feet tend to read better? Like, there's not, that's not causal that way. Well, would reading more make their feet grow? Probably not so much, right? So Yeah, so just keep this in mind. Association does not imply causation in either direction. It could be some other thing going on. Okay, so Thursday I'll talk about the handout.